welcome to this Agilent Technologies recorded webcast. We hope you find this webcast both interesting and valuable. If after viewing this recording you're interested in more, go to Agilent TM Webcast YouTube channel for more recordings or sign up for one of our upcoming live sessions at www.agilent.com/find/web_seminars. Now, over to the presenter.
Hello and welcome for today's presentation on how to test DisplayPort sync devices. Thank you, Emily, for the kind introduction. So the presentation for today is structured as follows. First of all, I want to give you a short overview on the DisplayPort application to set a common stage for all attendees. And from there, I want to look into the different levels of testing. And in particular, I want to have a closer look on the sync test. The most of the time of this presentation I'm going to spend on the composition of physical layer test signals for receiver tests. So I want to talk in detail about jitter and signal amplitude and things like that. I will spend a little time on test setups, but want to leave most of it to the application notes, and I will give you the links to download those documents for further reference. And certainly there will be a summary at the end of the presentation. So let's start with the DisplayPort application. Basically, DisplayPort is a digital video interface where digital data is streamed from a source device, which might be a computer, over a DisplayPort cable, certainly into a sync device, and that is most likely a monitor or projector. So the interface itself is mostly high-speed digital video lanes, and there's also bidirectional communication between the source and the sync device. That communication is quite essential in terms of powering up the sync device, negotiation, speed link, actually negotiation of sync capabilities, like, for example, resolution and supported speeds. And from there, I want to start to dive into the details of the interface. So basically, you have, as I mentioned, the main link, which is 1, 2, or 4 lanes. And this interface is really designed for performance. So this number of lanes is scalable. So one could decide to implement a sync device, for example, with only 2 lanes, because no more data throughput is needed because of the resolution and the supported video sizes. There are fixed link speeds for that main lanes, which is 1.62 gigabit per second or 2.7 gigabit per second. And the key thing here is it's independent from the display refresh rate. So this rate won't vary if the display refresh is changed. I mentioned already the bidirectional communication, which is also called the auxiliary channel. So that is a lower speed interface which goes in both directions. So for example, the sync device may also communicate back information to the source. This would allow, for example, to implement a monitor with an integrated microphone, and the sync could stream back digital audio data. However, in our context, it's mainly used for controlling the sync device when performing a receiver test. But we will have a look on that later again. So some more information on the technology. All lanes are differential 100 ohm terminated. They can operate at different voltages and different pre-synthesis settings. And this is all used to adjust the interfaces, for example, for different cable lengths or for different qualities of cable. Furthermore, the interface also uses spread spectrum blocking for reduced EMI. The next, I want to have a closer look at the receiver, and I want to clarify the term what the task of the receiver inside a sync device is, because later on we want to look at the receiver and want to see how to test the receiver in that device. So the task of the receiver is to take the electrical signal coming in its interface and extract the digital content from that information. And since the transmitter is not ideal and also the cable is not ideal, this signal might look pretty bad. Or using the words a typical word in the physical layer test, the eye of that signal is almost closed. And therefore, the receiver integrates several subcomponents which help to extract that information from the signal. There's an equalizer inside, which you can see here. There's a limiting amplifier inside. There's a flip-flop which samples the bit. And there's a clock recovery integrated, which is supposed to recover the clock from the incoming data signal. And all those components can be stressed by a controlled physical layer test. So this already concludes my introduction into DisplayPort and the application. And next, I want to have a closer look at different levels of testing, and I want to, in particular, look into sync testing. So first of all, and I have to apologize for the slide. Actually, this should be a monitor here, but you can hardly see it right now. So I want to have a closer look on the user observable effects caused by receiver problems. So how do you observe that a sink or the receiver inside the sink has a problem? And that could be, for example, that a sink does not work together with certain sources. It may work with a pretty good transmitter, so maybe one PC works fine, and maybe a little less good transmitter, which might be different PC, has a problem with that monitor. The same could be true for a cable. Furthermore, a sink could also struggle with different cable lengths, and especially with long cables. And during speed negotiation of between source and sink, the sink may not synchronize at high bit rate, which is 2.7 gigabits per second. Or in the end, you could also see a noisy image, which reminds you maybe about the old days of analog TV. So you could also observe bit errors in the digital data as a noisy image. So how to test a receiver then? So the most easy thing you could do is an interoperability test. So you just go to a store, buy a couple of source devices, a couple of cables, and then you just try out the combinations. And if everything works well, you kind of passed your interoperability test. However, the confidence of that test is not very high because another source device could come up or another cable could show up, and with that, it doesn't work. On the other end, the effort is pretty low. I mean, there's no costly instrument involved, and in fact, many standards do interoperability tests. In DisplayPort, VISA looks a lot on compliance testing, which causes some higher effort because test instruments are involved for compliance testing. So for each product, it is verified whether the product is within certain specification limits. And for that, several test points are picked, and the product is tested against these test points. All those tests are described in the so-called compliance test specification, and if this test is passed, your product or your sync device will get a DisplayPort logo in the end. So the confidence of a compliance test is much better, and on the other end, also the effort is higher because test instruments are needed. You could also go beyond compliance testing in doing a characterization test. The difference, or the main difference, is you don't pick certain test points to test against, but you just drive your product against the limits of its own limits, and then you verify whether these limits are beyond the limits given in the specification. So by doing that, you characterize your product, and this is very often done by silicon designers, and this would also help in finding out if an end-user product has a problem. So the effort is not higher in terms of test equipment, but it consumes more time to run those tests. However, the confidence of characterization tests is certainly the best confidence you can get for your product. So I talked about test equipment, and I want to have a closer look on the equipment needed if you go beyond interoperability testing. And the test equipment can be classified in three groups. One group of test equipment focuses on source device testing, one on cable testing, and one on sync testing. And those instruments or test instruments are connected to the interfaces of your products. So if you test the source device, you will connect to the output. If you test the sync device, you will connect to the input. And if a cable is tested, you use the connectors on the cable for testing. The source device is typically tested with an oscilloscope, and there is some compliance software which automates and simplifies those tests. And for controlling the test, which means doing the handshakes on the auxiliary channel, there's an auxiliary channel controller used to, let's say, control the source device. And the same is actually true for the sync testing. Maybe we jump to the sync right away. So when testing a sync device, not the signals coming out of the product are tested, but the signals running into the product need to be controlled, and then we need to find a mechanism, and I will talk about that later, how to detect problems when receiving that signal. Products for generating those signals are typically bit error ratio testers, and we have here a JBERT or a PARBERT, for example. And again, I mentioned it before, there's an auxiliary channel controller needed which controls the device, and then in terms of testing a sync also reads back errors. But as I mentioned, there will be more information on that later. And certainly there's also test automation software for controlling all the instruments and creating test reports. I haven't talked about the cable testing yet. A cable is a passive device which can be tested with either a TDR measurement or with a vector network analyzer, and you see the instruments for that down here. So from here, I want to have a closer look on receiver testing. And I mentioned you cannot measure a signal coming out of the receiver because the receiver does only receive signals. So you have to create a signal which you send into the receiver, and then you need to make sure that the receiver could understand it correctly. So what we do in receiver testing, we create a pattern with an impaired signal or impaired signal integrity, which means poor timing maybe, or small amplitude. And then we check whether the receiver, or we have a look at the pattern which was received by the receiver, and then we compare it against the original pattern that was sent out. And by this comparison, we get the bit error count. And then we could play with jitter or with other signal settings, and then we could check the error count, whether it changes or not. So the problem in DisplayPort is a sync device has only a receiver, so there is typically no data coming out. And that doesn't allow to use a bit error ratio tester streaming data in and capturing what is coming out. So therefore, DisplayPort standard has added a requirement for receivers to integrate an error counter for one specific pseudo-random bit sequence, which is also called a PRBS7. So there's a counter integrated into the receiver, or actually into the sync, not into the receiver, which is PRBS7 aware and can capture errors in that pattern. And this pattern is then being used for receiver testing. So this is how a typical setup could look like. You have your sync device here with the receiver, which has to be tested. And right here you see the PRBS7 error counter. So we are not using a cable for testing a sync device, but a test adapter, which splits the DisplayPort lanes into the high-speed data lanes and the auxiliary channel. And then we connect the high-speed data lanes to a bit error ratio tester, which creates or sends the pattern with all the signal impairments. And then we use the auxiliary channel to do link training, to power up the device first, to link training, speed negotiation, and then in the end, while the test is running, also reading back the error counter. So the error counter is in the end read back by the auxiliary channel tool. So this is a high-level overview how receiver test is being performed. I indicated a lot that there's some link training involved, and this is something I want to explain here on this slide. So the first step in the test execution is actually two steps of linked training. The first one is the so-called receiver frequency log phase. And what you do here, you send a clock pattern, a high-speed clock pattern, which is pretty easy to capture to let the integrated clock recovery of the receiver synchronize on that pattern. Certainly the data rate is supposed to be exactly 1.62 or 2.7 gigabit, but in the real world, transmitters are always not that precise, and therefore the clock recovery needs to synchronize on that. Once it's synchronized, the next phase is the symbol lock phase. The purpose of the symbol lock phase is first of all to train the equalizer, and then also to find the beginning of the pattern. And therefore, there are sequences of 5 bits, 5 times the same bit in a row embedded in here and here, which let the sync device synchronize on those bits, and then it finds the beginning of a pattern. And after that, the receiver stress test is actually performed, which is sending a PRBS7 pattern. To be more precise, it's a PRBS7-1. Okay, so on the next slide, I have summarized the complete pass-fail criteria for compliance testing. So compliance testing is not only checking the error ratio with a certain stress signal, but it also checks whether a sync device can achieve frequency lock at all. And if that cannot be done within 5 retries, it also fails compliance. The same is true for symbol lock. And the same is also true for the communication over the auxiliary channel. So if there's more than 8 defers, which means the sync tells the auxiliary channel controller, please repeat, then the test is also failed. Then the PRBS counter is checked in a way that we send a random number of errors, and then we check whether they were properly counted. And after that, the bit error ratio for the stress signal is being tested. And all those 5 criteria must be met to get the compliance in DisplayPort for a sync device. Okay, so I mentioned I'm going to have a close look on the physical layer signals for receiver test. And I want to start with the definitions in the standard document. And to understand those definitions, there are actually 2 graphs in the main specification that give the jitter numbers for receiver stress test. One is the jitter tolerance curve, that is on the left-hand side here, which shows the peak-to-peak jitter over a frequency range. And you see the frequency on the x-axis here and the peak-to-peak jitter on the y-axis in that diagram. The way how you have to read that diagram is that for each frequency you see a maximum of allowed TJ, which the receiver has to be able to deal with that. And how that works, I will explain in a minute. Further, there is another diagram shown on the right-hand side, which is the receiver eye mask, and that gives the minimum eye opening a receiver has to deal with as well. So you may wonder, this is less than 1 UI. Actually, you see on the x-axis there's exactly 1 UI, 1 unit interval, and this is the amplitude. And you see here in this diagram, and the higher frequency range, there's maybe this aligns well with the eye mask, but in the lower frequency range, there's more jitter, and this is actually the 1 UI curve here, and it goes even above 1 UI. So how do these 2 graphs match in the specification? And that can be explained in having a look inside the receiver. Inside you see the clock recovery I talked about before. The clock recovery has a certain closed loop bandwidth, which means it can actually follow low frequency jitter, and by that it kind of filters the low frequency jitter. So you see the minimum PLL loop bandwidth in here, which is 20 megahertz for a high-speed clock pattern. So if the jitter gets below that, and I'm calling that low frequency jitter in here, the clock recovery can follow the jitter, and it actually filters the jitter. So the jitter seen by the flip-flop for sampling bits is really always the eye mask you have on the right-hand side. And the eye mask actually shows exactly the horizontal eye opening matches exactly the flat line in the high frequency area here. So that is how to read the jitter definitions in the standard document. And it also indicates that for testing, we have to use high amounts of low frequency jitter to stress the clock recovery. And we may want to also use small amounts of high frequency jitter to stress the flip-flop in here. And this also allows us to analyze what's maybe going wrong in our receiver. I have one example in here how to derive the jitter mix for compliance testing. And I have one example here because there are multiple test points which actually allow for multiple, actually there are two curves in the specification, and also the ISI numbers are different. So let me just go with the example I'm having here, which is high bit rate at test point 3. And the standard document defines constant jitter for test point 3 at high bit rate, which is ISI of 161 milliUI and random jitter of 162 milliUI peak to peak. Those two types of jitter have certainly spectral contents, but are assumed to be frequency independent in that calculation or in the way to construct the jitter mix. So I have put in here the ISI of 161 milliUI, and don't be confused. Actually, the x-axis here is already 100 milliUI. And we have another 160 milliUI of random jitter, and this leaves some gap between that random jitter and the maximum peak-to-peak jitter. And then we can add sinusoidal jitter to reach the maximum total jitter of, for this point, 1,227 milliUI. And this is certainly more low-frequency sinusoidal jitter than, for example, over here. So if we decide for 100 megahertz sinusoidal, then we will end up with only a TJ of 491 milliUI. So that is how the jitter mix is derived for DisplayPort compliance testing. And there's one more thing I want to highlight here. You can certainly start calculating the difference between ISI plus RJ and the total jitter, but in real world, there is additional noise in your system, and there will be additional physical effects, like, for example, crosstalk, which also have to be accounted in the total jitter. So when mixing the jitter, SJ needs to be calibrated, or actually you calibrate TJ to fill the gap with SJ. So let's have a look at the next slide to show you all the things which need to be considered when composing the impaired signal. You saw that curve before for high bit rate at test point 3. There's another curve for reduced bit rate, which looks slightly different. And I have noted the total jitter numbers from that curve for certain frequencies. And if we change the test point, actually we have different ISI numbers which account into here, and therefore those numbers here need to be subtracted by 470, and the same is true for high bit rate with minus 17 at TP2. So what's about these test points, TP2 and TP3? Those are defined in the standard, and they define at which test point jitter is measured. And unfortunately, this is not easy to see in my presentation here. But for example, in a standard source sync configuration with a standard plug-to-plug cable, the test point 3 would be here. And this would be a test point for receiver testing. So there are different sync devices where this test point is not available. For example, there's a sync with a cable connected. So we call this a tethered sync, and it has a cable which plugs directly into the source. And for this, so those sync devices have to be tested at TP2. So here the ISI numbers, for example, are different. There are also sync devices which have an attached cable, but not a plug, but a slot connector. And these things have to be tested with or are typically used with an additional cable, and therefore TP3 applies to this test point. The last type of sync devices are actually something which is called hybrid devices, and you could say these are maybe active cables. So a hybrid device typically plugs directly into a transmitter and has directly a receiver connected. And then there's some sort of interconnect means between another transmitter, and you could think, for example, of an optical connection between that receiver and that transmitter. And this would plug again into a monitor, and the hybrid device would be something like an optical cable. But when testing a hybrid device, you would test the receiver inside that device. So, in summary, there's different jitter tolerance curves, and there are different test points, and now there are different stress components in a signal which are added together to stress the receiver or to stress the receiver in a sync. These components are summarized here. This is spread spectrum clocking, inter-symbol interference, random jitter, sinusoidal jitter, crosstalk, the transition time of the signal, and the signal amplitude. And I will have more slides on each component, so I will explain more in detail what is behind that. But you should take from here that some of those are actually kept constant in compliance testing. For example, spread spectrum clocking is constant. Inter-symbol interference depends on the data rate and the test point. Random jitter depends on the data rate only. Sinusoidal jitter is calibrated to fulfill a certain TJ requirement, and it depends on the data rate and the SJ frequency because of that curve, and it also depends on the test point. The amplitude depends on the data rate and the device type, which is different. So we have different amplitudes for all those types here, and even though this is TP3 and this is TP3 and this is TP2 and TP2 here, we have different amplitudes for those devices. The crosstalk amplitude depends on the data rate and the device type. Transition times are kept constant for compliance testing, and the signal amplitude depends on data rate and test point again. So quite some calibration effort, and as I promised, I do have more slides to talk about each single component of the stress signal more in detail. So the first thing is spread spectrum clocking. This is an intentional effect being actually generated by the source devices, and the idea is to reduce EMI emissions. So a transmitter is supposed to downshift its clock by a triangular frequency modulation between 30 and 33 kilohertz. In the compliance test, we only test the 33 kilohertz. When testing the receiver with SSC, we actually stress only the clock recovery. For the receiver, this is a very low frequency, 33 kilohertz periodic jitter, and the clock recovery has to be designed to follow that kind of jitter, and normally you won't see any errors from that. The next one is inter-symbol interference, which is the channel effect. So a lossy channel may cause more inter-symbol interference. A high-quality cable maybe cause less, but it also depends on the pattern. So that is actually already the second bullet here. The detailed requirement for compliance testing is to use different amounts of ISI for reduced bitrate and high bitrate, and also it depends on the test points. For compliance testing, we decided to implement a reference channel as an accessory, and this is therefore being added to the test instruments as an external accessory to have a very well-calibrated way to introduce that channel effect. Now I want to talk a little more detail about the random jitter. Random jitter occurs in the transmitter. This is not a wanted jitter, and it's mainly caused by thermal or noise effects inside a transmitter. It is important to know that random jitter is statistical by nature, so it means random jitter is typically not bounded, it's unbounded. So what bounded means is, or to explain bounded, we should have a look at the distribution of random jitter. This should be a Gaussian distribution. Unfortunately, it didn't come out well when drawing that curve in PowerPoint. But so this should be a Gaussian distribution. And what you see here, the most events are actually in the middle, and only very few events appear when you go towards the tails of the Gaussian curve. And unbounded means this never becomes, or this never gets zero. So even if you go very far out on that curve, you always will see some very rare events if you test long enough. So the opposite of that would be bounded, which means at a certain point of the Gaussian distribution, you just stop, and there won't be any events which go further out. And that is interesting. This is important to understand when testing towards a certain bit error ratio, because if you test for a certain time and you have bounded random jitter, you won't see any more events. However, if you have an unbounded Gaussian distribution, you will see more rare events. And I have a screenshot on that on the next page, and I think that will explain it a little more in detail. So the requirement for compliance testing is to use a random jitter of 7.9 milliui of RMS, and the RMS value is actually, you could say that's the 1 sigma value. So that's the value where you have the one here touching the gauss, and then you have a peak-to-peak value for 6 sigma projection. That is defined by DisplayPort, and you see that would go up to here in the Gaussian distribution. And what you see already in that graph, if you have a bounded random jitter which goes up to 5 only, that won't be an appropriate test anymore. So you have to be very careful when selecting your random jitter source for that. And finally, I want to highlight that random jitter only stresses the sampling flip-flop inside the receiver. So the clock recovery may be able to track some very low frequency components of the random jitter, but usually it's only stressing the flip-flop. So I promised some screenshots. Here they are. So this is an eye diagram on the left side of a random jitter measurement, and you see in the middle, most of the edges are actually on top of the Gaussian distribution, and the more you get towards the tails of the gauss, the less events or the less edges you see in that eye diagram. And this can also be observed in the BER scan. And as you can see, the slope here is constant the more bits you measure. And if you had a bounded random jitter, this would stop, and then it would be just a straight line down to whatever bit error ratio you're measuring. So moving ahead, the next jitter type we're going to introduce for receiver testing is the sinusoidal jitter. And I talked a little bit about it when talking about the jitter tolerance curve. Sinusoidal jitter is not really a real-world phenomenon. But it's a very controlled way to test receiver performance at a certain frequency, because you can set your sinusoidal waveform to a certain frequency, and then you stress your receiver only at that frequency. And by that, you can pick a point on your jitter tolerance curve to be stressed or verified. At lower frequencies, it stresses the clock recovery. At higher frequencies, if you go to the right side in that graph, so if you have a frequency above the loop bandwidth, you only stress the flip-flop inside it. So for compliance test, DisplayPort has decided to pick a couple of frequencies for testing, and those frequencies are 2, 10, and 20 megahertz at reduced bit rate. So one is in a very low frequency area, one in between, and one right at the PLL loop bandwidth. And only at high bit rate, we have picked another frequency at 100 megahertz to check the other area. This is based on experience, and mostly you see receivers struggling when the clock recovery is being stressed. In this area, in the high frequency area, the clock recovery is not stressed anymore, except maybe the spread spectrum clocking. I mentioned before, you don't really add a certain amount of Sj, but you calibrate Tj, and that process will be explained later. Just a quick screenshot for sinusoidal. You see it's well bounded. So with your waveform, you set the limits for the edges, and the edges in the eye are well distributed from left to right. And also in the BER scan, you see the eye closure is already there right after you measured 100 bits. So if you measure down to with a higher sample size, you usually don't add more jitter from the sinusoidal interference. Okay, the next is a crosstalk requirement, and this does not mean we add crosstalk or something which simulates crosstalk to the lane under test, but we add an aggressive, or we send an aggressive signal to the adjacent lanes. So in the example shown here, we stress lane 2, and then we send an aggressive signal to the lanes next to it. And if there's some unfortunate PCB design or some unfortunate silicon design inside the receiver, you will see crosstalk effects stressing the receiver. So this is really some test which stresses the sync device as a whole. But it's added to the receiver test, and especially to the compliance test. Crosstalk causes timing and amplitude stress, and I have an example on the next slide. And therefore it accounts into jitter. That's why it has to be accounted into the Tj calibration, and also into the amplitude. So that has also to be considered there. And this is well explained in the compliance test specification in the MOI documents, how to calibrate that. So, but basically, we use a 0011 clock pattern, so half-date clock pattern for the compliance test. On this slide, I have a little example for crosstalk, which is actually from a real device. So I'm sending a PRBS 7 pattern to one lane and a high-frequency clock pattern, so that's not the compliance test clock pattern, to the adjacent lanes. And you see the clean PRBS here and the high-frequency clock pattern. And I may have forgotten to mention that on a previous slide. One requirement is that that clock pattern is not phase-aligned. So you see the clock pattern moving over half of the UI of the PRBS 7 pattern. So what you measure at the receiver pins on the sync device board is a waveform which looks like this. And you see how the crosstalk adds up on the amplitude, but also causes additional jitter. And on the right, you see the resulting eye opening on the sync device board. So this is really from crosstalk on a real board. So crosstalk has to be added for the compliance test and should also be considered during characterization. There's a transition time requirement. I don't want to spend much time on that. Basically, it's the rise time or fall time of a signal. And for compliance test, the aggressor has to have 130 picosecond. And for the stress signal, there's a range specified. But if we keep close to the word of the specification, we should also use something which is close to 130 picosecond for receiver testing. Basically, transition times cannot be adjusted by the generator, and therefore we use external accessories to slow down the edges of the setup. And you will see that in the setup diagram just a few slides later. The signal amplitude requirement is to calibrate using the eye opening at a 50% point, and this is a pretty clean eye. So usually in receiver tests, this would look much worse. This is only for illustration purposes. And there are different calibration requirements in compliance for reduced bit rate and and high bit rate, and test point 2 and 3. So you see these eye openings are quite different. So this finishes my physical layer basics section, and now I want to talk a little bit more about the test setups and about the calibration procedure. And this pretty busy slide gives you the basic concept of calibration. So I mentioned several times that we need to calibrate sinusoidal jitter, we need to calibrate the amplitude, and the way this is done is we have a pattern generator with some accessories, which are basically the transition time converters and the ISI, and we run the signal into a test adapter, and then we plug in the another test adapter. So if this is a plug, this is a receptacle. We certainly need to terminate the aggressor signals, and then we use a jitter measurement device for measuring jitter and the eye opening. There are actually two test points for measuring. And there's one which I would like to call measurement point A, and one which I would call measurement point B. And they're used for different calibration purposes. There's also a sequence to follow, and if this is a little confusing for you right now, this is very well detailed in the compliance test specification in terms of requirements, and also in the MOI document in terms of how to do that with the test equipment. So first of all, the rise fall times and the ISI are fixed by hardware because these are fixed accessories in the setup. And then first thing to be calibrated is the random jitter at calibration point A, so without the ISI and without the test adapters. And also using a clock pattern, this gives a more precise measurement. Then the aggressor signal is turned on, and actually the amplitude for that doesn't need to be calibrated because there's no ISI, so the amplitude we set with the pattern generators is really the amplitude being present at the test fixtures later on as well. So the aggressors are on, so we will see the jitter effects from here. And then the total jitter has to be calibrated at test point or calibration point B using a PIBS pattern. And once total jitter is calibrated, we also calibrate the eye opening. And once that is done, we just turn on the spread spectrum clocking on the pattern generator. And also here, the concept we are using with our pattern generators to generate spread spectrum clocking eliminates the need to calibrate it. Finally, suitable pattern generators for the setup shown here are the Agilent JBERT or PARBERT, and suitable jitter measurement devices on this side could be the JBERT again, or the PARBERT again, or an Infinium oscilloscope. So this is on calibration, and the setup looks slightly different for measuring or for testing the receiver later on. And I have a setup here with the Agilent JBERT B, but also the JBERT A can be used. And as you can see here, we removed the second test adapter for calibration and plug in our sync device. And in addition, we have now the auxiliary channel controller connected to the aux channel. And this auxiliary channel controller then is used for powering or waking up the sync device, controlling the link training sequence. And once we are sending the PIBS pattern for receiver test, the auxiliary channel controller reads back the integrated error counter. So it's really the combination of both instruments which is needed for sync testing. The same is true when using the Agilent PARBERT. This is shown on the next slide. So you see basically the setup on the right side is exactly the same. The only thing is you have the modular PARBERT system on the left-hand side generating the aggressor signals and the stress pattern. And since we are using two instruments for receiver testing, we have the calibration and the test sequence. Test automation is actually a big thing in receiver testing. So there's a test automation software which has the product number N5990A, which does automatically calibrate the setup, which does an automated compliance test. It does a characterization test, and it has all the expert mode functions which help R&D engineers debugging problems. The software automatically controls all instruments, so the operator doesn't need to touch any buttons on the instruments anymore, however. And the software gives guidance. For example, you need to unplug the test fixture up after the calibration is finished and plug it into a monitor. And in the end, you will get sophisticated test reports from the automation software. And there's one example on the next slide, which is a jitter tolerance curve. So this curve looks maybe very similar to the jitter tolerance curve given in the standard, which I had on my slides before. However, this is now the limits, but it's the same curve, but it's the measured limits of a product. And now you can compare those measured limits of a product against the specification. And you can also find weak frequencies, but in this example, everything looks pretty well. So this finishes my test setup section, and I want to quickly summarize my presentation before we enter the question and answer session. I'm a little behind time, so I'm trying to do it a little quickly maybe. I mentioned several times the compliance test specification, which can be downloaded for free from the DisplayPort webpage, which is actually a Visa webpage. And I mentioned several times the method of implementation document, which is the Agilent application note, which explains how to use the Agilent products, and that can be downloaded from the Agilent DisplayPort webpage. And in terms of the setups I've described before, the tools are factory calibrated, so they simplify some of the testing. However, there's still, because of the ISI, crosstalk, and other things, there's still some calibration needed. All key signal stress components can be adjusted during runtime, which helps a lot during debugging. So you can just turn a knob and then you change your random jitter level, for example. No need to load a new setting or a new waveform. This is just turning knobs at real time. All instruments meet or exceed the signal requirements. For example, the crest factor for the random jitter that I mentioned before. In terms of having a look at Jaybird, this is a one-box solution for the test. And you saw multiple PowerBird modules. PowerBird is a highly flexible solution, which also allows to test multiple lanes at the same time. And one setup actually does not only serve DisplayPort as a video standard, but could also be used for HDMI testing or for MIPI DeFi testing, which is a video interface for embedded solutions, for mobile solutions, which focuses a lot on power saving. All setups can be complemented with test automation, and all setups and the automation software are reviewed and approved by Visa. So these are certified products for compliance testing. So this is my last slide. So I showed you a safe path to get the DisplayPort logo and also explained how to characterize their products. I think what you should keep from today is that receiver compliance is not obvious, and signal integrity can be violated in many different ways, which then stresses different components inside the receiver. So it really requires to add all these components to find out the performance of your product. So to get the logo and to ensure full interoperability, it's required to do at least a compliance test. And I just want to ask you to master the signal with the appropriate tools to get reliable and repeatable results. You can find more information on the DisplayPort webpage, and I think that's finishing my presentation for today. Thank you for your attention, and we are now open for questions.
Great, thank you, Michael. So the floor is open for any questions. Alan, have you received any in chat?
Yes, there was one question related to how to get the presentation slides. And my recommendation is you can either go to one of the links shown here on Michael's last slide, and we will post them there within, let's say, the next 2 days. The other option could be that we just, if you chat in your name, we will directly email that to you. So if you just use this chat and send function and send it to my attention, I will, send you the slides.
We'll actually follow up with all registrants as well with a recording URL and the slide set PDF.
Okay. From the technical side, there was 2 questions. Question 1 was that there was an instrument which was set as an auxiliary channel controller, and it looked like another box from a company called Quantum Data. The question was, is that the same product, or does it just look like the same? Can you please comment on that, Michael?
Yeah, that's actually a very good question. So this product is actually coming out of a cooperation with Quantum Data. And the Quantum Data offers something which is more like a link layer tester. And this product is the basis for the auxiliary channel controller. But actually, both products are not the same. So the product, the auxiliary channel controller, adds some additional IP from Agilent. So there's another add-in card and some more software plugged into the product for auxiliary channel testing. So the products from Agilent can be upgraded by features from Quantum Data, and the products from Quantum Data can be upgraded with the Agilent auxiliary channel feature, but it's actually 2 different products. So it's not exactly the same thing. I hope this answers.
Okay, thank you. Okay, the second question was around the crest factors. The question was, could you explain the RJ a little bit more in detail? Where does bounded random jitter come from, and how does it affect my measurement? You said that this measurement could be potentially wrong. Could you please comment on that?
Okay, let me just go back in my slides to see to pick the slide that I used for that again. So, and well, the main problem is how random jitter is specified, maybe, or I mean, it's actually not the problem, but that's the key thing to understand. So random jitter is specified in a way that you have an RMS value, and then you have a peak-to-peak value using a certain projection. So if you have, and in my example here, I have a 5 sigma bounded RJ, but in DisplayPort we are asked to do 6 sigma. So you either set your RMS value correctly, which would be then the 8 milli-UIs here, but then your peak-to-peak value with your bounded source won't reach the won't reach the 97 because you have to go up to here. On the other end, you could also change the setting of your 5 sigma bounded noise source, and then to go up to 6. But then this would mean, and let me try to draw this, but then the shape would go, I mean, it would go up earlier here, and then you would see more, I'm sorry, this is really not easy to draw. So the shape or the Gaussian distribution would be different. And going to the eye diagram, let me see whether I can change the colors here. So if you change the shape of your Gauss, you would see more edges here with that bounded noise source. So you would be really performing the wrong test. So that's maybe why it's so important to have the right random jitter for as it is called out by the standard for receiver testing. And I'm not sure that I covered everything of the question, but I hope this explains good enough why the crest factor is really important. So the crest factor, and maybe spending 2 more words here, the crest factor is really of your noise source. It's really to how many sigmas it is bounded when having a look at the Gaussian distribution. And as mentioned before, for DisplayPort, this is using a 6 sigma projection. Other standards which look at a bit error ratio, target bit error ratio of 10 to the minus 12, this would be 7 sigma, for example.
Thank you for watching this Agilent Technologies webcast. For more recorded webcasts, subscribe to our Agilent TM webcast YouTube channel. All of our webcasts are held live. Interact with our Agilent experts in the live Q&A sessions and gain access to Agilent materials. To view our upcoming live webcasts and to sign up for free, go to our website, www.agilent.com/find/web_seminar.